Here we go. We know from the fundamental theorem of calculus for line integrals, looking at a vector field and determining whether it's a gradient or not is important. And we have this weird test, right? The weird test says identify f1. This is going to be x plus y squared. Identify f2. That's just the stuff next to j. That's 2xy plus y squared. Then take the partial derivative of this one with respect to y, and we're going to get 2y. Take the partial derivative of this one with respect to x, and we get 2y. They're equal. Now, we haven't even found the original function at all, but because this is equal to this, that's going to tell us that this thing over here actually is the gradient of some function. Now, how are we going to find that function? By taking antiderivatives and a little teeny bit of guess and check. Find the original function. Now, how am I going to do this? We know that there's a function that we don't know whose partial derivative with respect to x is x plus y squared. Now, what is that going to tell us? If we take the antiderivative of that with respect to x, we're going to get 1/2 x squared plus xy squared plus some stuff that has y's in it only. We also know that fy must be 2xy plus y squared. Now I'm going to take the partial antiderivative here with respect to y, and so I know that fxy here with respect to y, yes, we're going to get xy squared with respect to y. Yes, plus 1/3 y cubed, plus some stuff that might have some only x's in it. Now what we have to do is just look at this and say, minimally, what does f of xy have to have in it? Well, it has to have a 1/2 x squared in it. It has to have an xy squared in it. Now it doesn't have to have 2xy squareds in it. This thing right here and this thing right here says it has to have one. It does have to have 1/3 y cubed in it. And I think that's actually the thing we're going to do if I try to check to make sure we're close. If I take the partial derivative with respect to x, I get x plus y squared like I was supposed to. When I take the partial derivative with respect to y, I get, let's see here, 2xy plus y squared like I was supposed to. And that's how it usually works. We check to see if it has, if it is the gradient of some function. The function we usually call the antigradient because we get it by taking antiderivatives. And then we actually have to piece together the information that we have. This is not adding, this is just piecing together the information like a detective and trying to find minimally what the function actually has in it. Now, by the way, it could have a constant as well. I'm not going to worry about that. But that's our first example. Let's just look at one more example. It's a simple example. It's one we've looked at almost many times. And I'm going to say, is this vector field, I want minus yi plus xj, a gradient? Well, remember how this works. Identify f1. f1 is just the stuff next to I, that's minus y. Identify f2. f2 is just the stuff next to j, and that's x. Then I want to take the partial derivative here with respect to y. I'm going to get the partial of f1 with respect to y is minus 1. And then I want to take the partial derivative of this with respect to x. I get the partial derivative of f2 with respect to x is 1. Now, if this was the gradient of something, those two would be equal. Because this would be fxy, this would be fyx, and those are normally equal. But they're not, right? That's going to tell us that this vector field, let's write it as a conclusion. This vector field is not the gradient of any function. Now, generally speaking, that's bad news, because that means we cannot use the fundamental theorem of calculus for line integrals to do this. We're going to ask, every time we actually see this vector field, we're going to have to start with parametric equations and just set up the normal way. Now, one final note, let's say I just ignore this and I try to find an antigradient anyways, a function whose gradient is equal to this. Now, how would we do this? If this is actually the gradient of something, that would be fx. And so I would take the antiderivative of that with respect to x, and I'd get minus xy. If this was the gradient of some function, that would be fy. I take the antiderivative of that with respect to y, and I get f of xy equals xy. Now, how am I supposed to combine those two things together, right? If it has to have a minus xy plus y stuff, and it has to have an fxy equals xy plus x stuff, it would have to have minus xy plus xy plus other stuff that all goes away when we take the derivatives. Well, that would say basically that the only thing we can have is 0. And it's certainly not true that the derivative of 0 with respect to x is minus y, and the derivative of 0 with respect to y is x. So the test itself shows us there wasn't a gradient. When we actually try to find the gradient, we get something ridiculous looking like that. And so it does not have a gradient. I'm sorry, it does not have an antigradient for two good reasons.